Hey everybody, today I'm going to talk about organic chemistry. I'm going to give you a little bit of background information that you'll need for the AP test. I am in no way going into any great length or detail into organic chemistry. This is a huge science, it's a huge part of chemistry, and it would take quite a long time and a lot of practice to go through everything you would need for if you're an organic chemistry course. So this is a very introductory portion. I'm just going to give you the general information you need to do well on the AP test. To be honest, a lot of the stuff they give you the information for, if you understand Lewis structures, you should be able to determine a lot of these structures without understanding organic chemistry. And also, it just kind of helps, I guess, just to have a little bit of background on some of the organic molecules and the naming systems and stuff. All right, let's take a look at the nomenclature. Well, this is actually getting into the nomenclature. The first thing we need to know is something about the three different types of structures you're going to see. All right, so you're going to have what are known as molecular structures, and this is just summing up the elements that are in the molecule. There's no other information other than how many elements there are in the formula. You get into a little more detail with the structural formula, where we take those two carbons and we put them in their structure. Now, a lot of organic chemists don't write these dots in here. I kind of drew these in. I had a little trouble with the video, so I had to redo it, and I didn't erase this slide, but that's okay. The dots here, you should put them in. I would recommend you do, but a lot of organic chemists don't put them in, so you might not see them in some of the drawings. But don't forget that nitrogen has that lone pair on it as well, just like the oxygen does. Carbon will never, it is very unlikely that you'll have carbon with a lone pair of electrons, so you should never draw something like this where you have carbon with a lone pair of electrons above and below, and you do something like this and join it to another carbon. That is not going to happen. The only time you're ever going to have a lone pair on carbon is in triple bonded with oxygen. This is the only time I can really think of where you would have a lone pair on the carbon. Otherwise, carbon is always going to have bonds around it. It can either be four bonds that are separated, are by themselves. So you'd have four bonds, 1, 2, 3, 4. Sometimes it does a double bond and you get two of these. Sometimes it does a triple bond and you get one of these. Sometimes it does a double bond, but notice that all of these have bonds around the carbons. Okay? No lone pairs of electrons around it. Then we get to what's called the condensed structural formula. Now, a condensed structural formula takes this structure and kind of combines it with number 1 and tries to mimic that shape a little bit. So you would have that first carbon with 3 hydrogens, so carbon with 3 hydrogens around it. Then you have another carbon with 2 more hydrogens. Then the oxygen comes next with another hydrogen. So the hydrogens are kind of like those hydrogens that are just kind of accompanying the element before it. All right, so that would be your types of structures. Now what I drew here was a lot of times organic chemists not only drop the electrons out, but they drop the hydrogens out. So instead of drawing hydrogens in here, it's just kind of understood that hydrogens are going to fill in those spaces. I don't think that they're going to do that to you on the AP test, but it is something to know. I've never seen it, really where they've drawn them like this. And because of that, they tend to just not draw the lines even. You'll just get the carbons drawn in a line fashion. Okay, without the bond, you would have to imply that there's hydrogen, 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 hydrogens all around. And the other thing they tend to do is they just take this structure and they put it in this form, because that carbon is going to have a repeating pattern, this up and down thing, where this is just called a line structure. Now, it doesn't really have the dots on it. What it would literally look like, because I drew those dots, and there would just be up and down, just a upside down V. That would be that structure there. Not too big of a deal. That's where you might see this kind of drawing here, where you got these carbons looking like this. That each of the corners is where the high carbons are. So you got a carbon here, carbon here, carbon here, carbon here, at each of those corners and intersections. All right, just in case they come up, you kind of get an idea of what that looks like. All right, now hydrocarbons are broken into two groups, acyclic and cyclic structures. Acyclic are the ones that are straight chains. So you got something that looks like this, where the carbon is just kind of repeating itself over and over again. Okay, with the carbons just kind of doing something like this in a long chain. Acyclic just means a long chain. Closed or cyclic structures are ones where you have that ring structure where it kind of repeats itself over and over again. You get something like that, you get something kind of like this, where you have structure that looks like this. So you have various different shapes that you can get for your cyclic structures. They just kind of loop around each other, so this carbon joins to the carbon on the other side. Now, acyclic hydrocarbons consist of carbons essentially all with the hydrogens on the outside. These are referred to as saturated hydrocarbons. I'm going to talk about the acyclic ones first. Now, they're broken up into saturated hydrocarbons because they have all of the carbons all kind of surrounding them. Now, alkanes are going to be all single bonds, and this is why it becomes a saturated hydrocarbon, because you get as many hydrogens around that carbon as you can. So this would be single bonds are all in this one. And as you can guess, the alkene is going to have a double bond, okay, and the alkyne is going to have a triple bond. And as you can tell, yes, it is alkanes, alkenes, and alkynes. It is only different by that one letter in the name. These are unsaturated hydrocarbons. This one is a saturated hydrocarbon. All single bonds, it has to have at least one double bond, it becomes an alkene. At least one triple bond, it becomes an alkyne. Alright, let's continue on here. Let's look a little bit more closely at the nomenclature. Alright, so this is the basic structure of our nomenclature. We have a prefix, a parent, and a suffix. Now the parent is going to give you the number of electrons, gives you the number of carbons in that structure. That's the function of that parent. So it tells you what the backbone of the carbon structure is going to be. Alright, and I'll show you how you're going to get that in a little bit. The suffix tells you whether you have an alkane, an alkene, or an alkyne. So there's ethane, ethene, and ethyne. Okay, there's three different types of those and they're all F because it's the same number of carbons. All right. Then the prefix is going to tell you some information about where functional groups or substituents are going to be placed in that hydrocarbon chain. All right. All right. I'm going to give you some more information on this, but this is the general pattern. You got the parent, suffix, and prefix. Parent, number of carbons. Suffix tells you whether you have double bonds, triple bonds, or single bonds, and the prefix is going to tell you where those things are located in the structure. So let's just look at some data here. Alright, so if we're going to name these, all you do is the name is based on the length of the chain. And we add the name ane at the end. So meth is our first prefix. So we have meth, eth, prop, bute, pent, hex, hept, oct, non, and deca. Okay, so that would be our name. Now notice that once we get to 5, it just goes back to the Latin prefixes. So we have meth, eth, prop, and bute for 1, 2, 3, 4 number of carbons that are in the chain. So this is methane, this is ethane, this is propane, this is butane, and then we get to pentane, hexane, heptane, octane, nonane, and decane. Okay? Now notice the boiling temperatures. Boiling temperature goes up as we make the chain longer and longer because the London dispersion force is increasing as the number of electrons increase in each of those hydrocarbons. And these are the easiest to name, so I wouldn't worry, this is probably a good place to stop, I guess, in the nomenclature. I'll show you the alkenes and the alkynes. But they get a little bit crazy, but not too bad. So if we have 6 carbons in our structure, we're going to call it hexane. Ane means that I have just all single bonds. So just 1, 2, 3, 4, 5, 6, and then put the hydrogens all around. Okay.